from Romania, from our favorite artist, Mr. Kittel here. I have a very interesting project, but before showing you the interesting part, I have to show you how everything started, how a little bit, if you want, like a little bit of history of how things progressed to the point that I am right now. You can see it here on the side and here the circuit diagram, a little bit of it. I don't want to show you right away. I'm only hint you, but it's a very interesting project, and you will like it. Probably. We will see. So the first project that I want to show you, and that I made already, let me bring up this guy. I made a counter, but I made that counter with LED displays, like you are seeing here. These are 7-segment LED displays here. So I have both of them, common anode and common cathode, and I use this common cathode because if I have to use common anode, I had to insert NOT gates to equalize everything, and yeah, it's not pretty. So I had a project when I used this display 7-segment LED display, all right, with a 4033 integrated circuit, and this IC is counting only up, and that's it. It doesn't count down like the chip that I'm working with right now. So this is an old project. I already built this. I will show you the actual project, and this is what I'm having here is cascading. I should write it somewhere. It's pretty much the same thing that is numbering from 0 to 9 and displaying on the LED display that I'm having here, 0 to 9, and then it's cascading to make 999 pretty much, and then when it's clocking once again, is getting back to 0 and starting from 1, 2, 3 to 999 again. And it's having a reset button. If I'm reaching some number, I can reset everything to 0, and I can start again, but only counting up. And I didn't like it. I mean, it is very, very practical, a very practical counter. I love it. I actually love it. But I don't really like it 100%. This is the actual counter that is up and down, 4110. And it is here, not showing here, 4110. It is here in this diagram. You see it here. This is the project that I'm working right now with this counter that's counting up. You can see actually here, clock up and clock down. You see, that's the difference from this chip 4033, which is very, very easy to work with. I mean, that's why I love it. It's very, very easy, and it's doing the job. It's doing the job perfectly. Okay, so I will go to the table and show you the actual project that. Oh no, I wanted to show you the 3D model that I built, and I showed this already, all of this, and I built everything as you can see. This is only one module here. What I'm having. This is the actual project I'm having right here. This guy here. And it will be, and it was in this configuration, in this A configuration that you are seeing here. What I'm having here, I'm having different designs, A, B, C, and I choose or stopped to A design that I'm having here, and I used 3 LEDs, LED 7-segment displays, you know, and it was this mess, and this is how I built it. Of course, this is like blown up here, but in reality, it was all squished together on the cardboard, of course, on cardboard, and this is the principle, the real circuit that you are seeing here in 3D. It's the real circuit that I built it in reality, exactly like this. And of course, it was having 3 modules, not 2. But I only model 1, and then I made the other 2 and make the full 3. All right. Okay. Now that's it for this part. So you understood. You get the idea how I started it, you know, and the reason of everything that I did. So I will close this. In my Windows, it's not okay. All right. I have 5 volts there already prepared, and here this is the real counter, and it's working with 5 volts. Also 5 volts here. This yellow wire is plus 5 volts signal wire, and this is the negative here, and that's it. And it's having a reset button here, and exactly as in the 3D model that I had there. Let me plug it in. All right, and here is the reset, how it's working. And if I'm pushing the clock at a higher frequency, if I'm giving it some speed, so this is emitting the signal, it's creating a signal, and this is reading the signal pretty much. And also the reset again, and if I'm holding it, it is showing 888. It doesn't matter, and but it is counting each clock that is receiving from there, and at the exact same speed as this guy is. You see, is clocking very fast, or very slow. So that's it with this project. It's that simple, right? All right. So you've seen the real project that I made with the 4033 chips, because I used 3 of them for each display. And as you can see here in the title, it says 7-segment display, but it's not really completely correct. 7-segment LED display, it should be here. But this was absolutely my first project doing anything, you know, important with a 7-segment display, like this counter. And it remained like that. It should be renamed as a LED 7-segment display or something. Now, this is the LCD, and I have 2 of them. I have a multiplexed 3-digit display. I can show you. I believe I have it here. This is how it's looking, like this. You know, it's very cute. But as cute as it is extremely hard to drive it. I couldn't discover how to drive it yet. But I will receive a chip that is dedicated for driving this kind of multiplexed LCDs, and hopefully that will do the trick. But the way I'm doing things more intuitively, if you want, and that's what I'm saying. That's why I'm saying it's very hard to drive with my logic and my knowledge that I have. The static LCD, it's very, very easy to drive it with my logic and the knowledge that I have. So that's the complex circuit, but I want to show you how I started. So I said to myself, so this is the first project. Actually, it's very simplistic if you want to. So make abstraction of all of this side, because everything, as you can see, is the same, is repeated, and it is cascading pretty much. What it's doing is I'm having four characters or 4 digits here, digit 1, 2, 3, and 4, or A, B, C, D, and they are all derived by one chip that is creating all the logic to display everything. But also it needs a driver because this is an LCD. You can see here in the title, it's a 4-digit static LCD. And let me show you his face. LCD here. It's this ADC. Yeah, you can see here the actual. This is all the datasheet that I have about it from the seller page. You know, this was the important thing, to be static and what voltage is working at 3 volts. That's it. These two things I actually needed to be sure how to drive it. And after I understood that is a static LCD and is working with 3 volts, then I worked everything from there up. So that's how it's looking. Yeah, I have specifically for this static LCD, I have this little circuit diagram that I made. I used two LEDs here, as you can see, opposite of one with each other. Because why opposite? Because the way this LCD is driven, the LCD is driven with a negative here, positive here, and then a switch, positive here, a negative down. So it's alternative. It's alternating the polarities, and that's why I wanted to see in slow motion when this is activated and if it's activated. And by using two LEDs in opposite directions, I can see that it is actually working. That is doing the job. This entire alternative driving of the LED. So this is the basic circuit that I is the first one that I made. If I couldn't figure out how to make this basic circuit, I couldn't make anything else. So this was imperative. Yeah, this is voltage regulator with a 3 volts output that I use it in my breadboards, and it's using 1 kilo here and 1.4 kilo here to give me a 3 volts output from 12 volts here, but I use 5 volts actually, not 12 volts on the input. So the output is 3 volts constant, which is good. So back to the circuit. So pretty much I will drive this LCD. Where are you? Actually, you know what? Open with pure rip, and I will put it like this. Like that. And close this. So this will stay on all the time. You know, whatever I'm clicking here. So this LCD that you are seeing here in the corner is having 4 digits, as you can see, 1, 2, 3, 4, 1, 2, 3, 4, and pretty much I'm replicating these digits of the LCD with this parallel LEDs put in opposite directions. This is a single segment. If you watched my previous movies, I already discussed these little details there. This is a bigger picture what I'm having here. So this is doing only one single and simple thing, is displaying numbers and counting up or down, exactly like the previous project that I made with LED displays, with the 3 LED display, 7-segment displays. And if I'm running this, as you can barely see the number, because here in the simulator I don't have this naked display. I only drive one. I was making a test, and it's that easy. It's very, very easy. You don't have to do anything like I'm doing here. You don't have to actually build a driver, an LCD driver. They have incorporated already that LCD driver. What I'm doing here, I'm doing the LCD driver because this is a bare naked LCD display, and it doesn't have anything. It doesn't have a driver, so I need to provide it a driver. So that's what you are seeing here. This part, actually, this part here, including this clock, LCD refresh, it says there. It should be LCD clock at 100 hertz. And this XOR gates here, which I have. This is a bit complicated because I have 2 of them, actually 3 of them. It's like this. It's a DIP chip, and this 7486 also a DIP chip like that as well, also like this. But I also have another model of 7486. Yeah, this is it. So you see it's SMD 5 pins, and it's looking like this, exactly like this. I can zoom in on it. A and B, it's a single gate chip. It's having one single gate, a power, 2 power pins. This pin 5 is positive 5 volts, and this is negative 0 volts. So pin 5 and 3 are the power pins. A and B are the inputs of the gate, and this pin 4Y is the output of the gate, and that's it. And it's performing this exclusive OR function or XOR. So I have, and I thought of it, and on one single DIP chip like this. One single, you can see it here as well, is having 4 gates, and I can use 1 4030 or 7486, doesn't matter, with 4 gates. So I will use 1, 2, 3, 4, and these are all 4 gates in one single package, one single chip. But these 3 gates, I can use them as SMD version, this guy here, and that's the plan. I will use different packages pretty much, but it's the same gate in all of them, I hope. And it should do the same job pretty much. Okay, so this is the driver, like I said, and probably for this clock, for this refresh at 100 hertz, this will be a constant clock. It will perform a constant beating, pack, all the time. I will not need to variate this frequency at all. I need it at a constant rate all the time, and I'm planning to making it with a Schmidt trigger gate. In this case, I'm have what I have in my arsenal. I'm having this NOT gate, 7414 NOT gate with a Schmitt output, and that's. But I can use whatever other gate that I have that is having that Schmitt trigger inside it. It can be a an AND gate, an OR gate, whatever that is having this specific Schmitt trigger inside it. Schmitt trigger. All right, so but this is the basic circuit of it. It is working here in the simulator, but with some bugs. That's why I put this switch here, because if I'm running it without the switch directly, it will crap itself. The simulator will crap itself, and it will throw its shit in my eyes. And we don't want that. This is another clock, and I plan either to make it with this 555, as you can see it here, or like this, but using a potentiometer like it is having already here. Here is having a potentiometer, and I will vary it a little bit the frequency. I'm not completely sure how I will make it. Probably this 555 clock that I'm having here. This is actually an outside clock. I don't actually need it in my circuit. This clock pretty much is getting the signal from this wire here, from whatever clock is outside of the circuit. So if I'm putting some sort of clock on this wire for this entire circuit that is here, it should display it. The numbers pretty much. So this is very optional, very extremely optional. And probably I will not include it, because in the other circuit I didn't include it. I only use it as a reference, if you want, something to clock automatically. So pretty much this is the circuit here. This is all the circuit, and it's cascaded. It's pretty much the same thing, doubled. And this is called cascading, and it's doing the correct order of numbering, pretty much like we are used to. And this is counting up and down. This is a function. This is the new function of this chip that the other chip 4030 doesn't have it at all. And that's why I'll use this fancy chip that I'm having here with this fancy display, LCD display, and they are totally new for me. Both of them actually. I only tested it, this 4110 chip. I only tested it on the breadboard, and it is working fine. It is working fine in the simulator as well, but I never built something serious with it. So that's why I'm using it in this project. This project is for this. Is for him. Is for this chip to use it, and also in the same time I'm shooting 2 rabbits in the same time, also using this LCD display. All right. So pretty much there is another face of the truth and of the reality. There are integrated circuits drivers for LCDs, and they are specifically designed to drive the LCD and having also a counter in them. But like my 4033 that I had before, they don't have extra options like this 4110 that I'm having here. This count up and count down. Those chips don't have this, and by creating this outside driver, pretty much, I am able to add very interesting integrated circuits from outside. The logic, I can change it whatever I please. I can play with the logic, and this is the logic made from 4110. This is a special logic that I'm implementing it on the driver, and the driver is actually making the display work correctly of the LCD. Pretty much, that's the extra bonus of this circuit. That's why I like it. That's why I build it, because of this extra customization that I can add, extra functions like the count up, count down function that other chips that are having inside all this driver for LCD, they don't have it. Okay, so this is the simple, what we are seeing here. This is the simple circuit, and I was almost on the point to start building it, this one. Then I decided, nope, I want something more, a little bit more. Save, no, I don't want to save you. So I will go here, and I made this a second save file. It's called the same name, but with a B on the. Imagine this was A, and next is B, C, D, and so forth. But at this point, it's only B. So this secondary circuit, I will not open it because it is already opened here. This is the circuit that I'm having. You can actually see it there. You see LCD B. It's the same file, and the complexity I've added is this lower part here. And all this is doing is a converter, pretty much. Actually, this is a converter here. It's converting. Is reading. Actually, is reading. Is expecting. Better said. When checks if 0 is displayed on the display here, but it really doesn't reach that far at that stage. It reads directly from the outputs of this 4110. And it is pretty much reading the outputs, and by reading it expects this kind of inputs here on these diodes. So these lines represents the inputs of these diodes, but also they are in the same time the outputs of this integrated circuit. Okay. So I build this circuit with these diodes to mimic, to input exactly this output at this stage when it's 0 right now. If I'm clocking once, now I clocked. Everything this guy transformed into 1, as you can see. Actually the 110 chip changed. I clocked this chip, and after clocking it, it changed the logic inside, and everything becomes something else. This pin number 1 is negative, and this pin number 2 remains positive. And as you can see it here, reflected here as well, but nothing is lighting up except when is reaching that 0. I can do whatever number I want, actually. These guys here, these diodes that are pointing towards the chip are expecting a 1, and this diode that is pointing towards the transistor is expecting a 0 here. And when everything is fitting perfectly, so all these diodes, when they receive a 1 and this last one receive a 0, it will open up this exactly like it's here in the next one. But if everything is positive here, and this is the last one is also positive, it will not work. If everything is positive, this is negative, but one of these guys is negative, everything will not work. So it's very, as you can actually see here, is getting two positives here. It should theoretically work, but it doesn't, because the current goes towards the negative, so nothing is blocking it. And I will not detail too much the functionality of this circuit. Suffice is to say that is working. All right, it is working. So what I did, I set it to 0. I can set it to any other number I want, if I want, but it's a convention. I made a convention here to open, to switch to 0. To switch this last output LED. This is a red LED. It is switch when the display is 0. So all these 4 converters are expecting a special order of inputs to lit up that output LEDs per each, and then all these 4 modules that I'm having here are then again processed. So this input from this guy here is expecting a 1 1 1 1, and when everything is 1 1 1 1, is lighting up this final output and also activating this buzzer. That's so I think you get it now. All this circuit that you see here, this converter is made specifically to activate a buzzer when everything is on 0. If I want to make it work for 999, I can do that as well, or 111. What it really matters is the order of everything, of these diodes here, and what they should expect here. This is hard-coded. This is like a constant. In programming language, we are using variables and we are using constants. And this, what we are having here, is a perfectly good analogy with a constant in programming language. This will never change. It will only expect one single thing, and it will activate when that thing will be true, pretty much. And the same goes for this guy here. Here I was thinking, I didn't check it actually, but you see here, eliminating any of these signal lines will result in the following. If only line 1, so this is, let me stop it. So this is the line 1 that I'm referring to. So these 3 guys, well, if I'm deleting them, let's make the test actually. I never did this test, I only thought of it. And, but let's see if it's true. If I'm deactivating all these lines, these diodes that I'm having here are not responsible for anything. Actually, I should probably link them to positive, maybe. I learned my lesson to not let anything floating, pretty much. Probably it's a good thing to link them to a positive rail, to have them as 1 1 1, and leave only this guy here changing. And this will dictate the output behavior. So when I'm playing it, of course, is positive because that LED is on. But when I'm clocking it, 1, 2, 3, 4, 5, 6, 7, 8, 9, and now when I'm clicking, it will activate both this guy and this guy. Bang! You see? So this is what I wrote it here. If only line 1 is active, meaning this line is active, but the rest are cut off, are not used at all, or better said, I'm not using the diodes at all. I'm not inserting them in the circuit at all. I'm just deleting them like that. If I'm leaving only one diode there with this input here, I can will beep from 10 to 10. So pretty much it will receive the signal from this converter that I'm having here. I can actually switch the line if I want, if I'm doing this to number from 100 to 100. But yeah, I can do that as well. Let me undo back and those diodes and the rest of the lines. And but that's the idea. I mean, you can play with the logic that you have here. It's very intuitive. The hard part is constructing it at the construction stage. But the logic stage that we are having right now is very, very simple. So if all this line, you read the text and you figure it out what it means already. All right. So, but my point was the observation that I did, that I made, is that if I'm changing the lines or the numbers of the diodes, or changing the wires from one pad to another, to other blocks here, I can actually change the timing of this final output and this final buzzer that I want it buzzing. So this is the more complicated, a little bit more complicated. It's a lot of diodes here. As you can see, it's a ton of diodes, and I don't really like that there are so many diodes, but well, they are cheap enough, I suppose. They are cheap enough, and they can be used. A very, very important thing, if you number them, let me go here. If you number them 1, 2, 3, 4, 5, 6, and 7, they are not 8 or 16 or something. They are specifically made for how many outputs I need to read, pretty much. I need to read 7 outputs from that chip, so I'm using exactly 7 diodes. And that's another detail that I forget to mention it before. So this is all the cool circuit, the cool logic of this entire circuit that I'm already having here. So it should be a very cool circuit in the end, hopefully. I already started the circuit board in 3D. I modeled, here is the model of the LCD. I put its name there. But let me actually rotate around that text to actually see the colors. You see, I have some color numbers here, exactly as in my diagram that I'm having here. So exactly like here, you see, let me position this. So I kind of mimic this color coding that I made here on this diagram here, and I put it here in my 3D version as well to be simple to follow. But I started to make something. I'm in the process of building this circuit, and I am thinking if I will add each wire here in the 3D, because it will be a fuckload of wires, a fuckload. And and I made this clock, LCD clock here, which it was a great help, of course, to make it like this in 3D and everything. It doesn't need too many wires, of course. But these guys here, the XOR gates that I'm having here, they will need a lot of wiring, a ton of wiring. And I'm not sure if I can do it here in 3D. I mean, probably I will make one with all the wiring, probably. I'm thinking, I'm not completely sure how I will make it here. Because it's a ton of time wasting. And I can do it in reality pretty fine, pretty well. I don't really need a 3D version for this. I didn't thought too much on this problem with the wiring. I will think about it later. So yeah, another interesting thing is that I had to model this LCD that I'm having here. You see here, this is the real LCD. I put this box because if I'm leaving the box with all this stuff exposed when I'm rotating in my viewport here, it's kind of getting very hard. Well, it's good now, but sometimes it's getting harder to. Is lagging, is creating some lags. I also modeled this multiplex, this little multiplexed LCD here as well to have it there. So this is my component list that I that I am adding with time. I'm adding with time, and I'm picking them up one by one and using them in my circuit that I wanted to make. Also, I modeled this guy here. This is the new XOR gate that I have with 5 pins, and it's a funky one. It's interesting. It's very small. It's the biggest problem that I don't like is that each of this small SMD gates is having. I have to supply it with power with VCC and ground, and it's a must. I cannot escape from this. But it's a bit annoying because it's extra wires compared with a chip that is having 4 gates in it, and it's a bit funky how we do it. But the small size of it, it's actually interesting. You know, like I arranged them here already, and like I said, I will use 4 per one chip, 4 gates per one chip, and 5, 6, and 7. You know, if you remember here, I have 7 gates, 1, 2, 3, 4. So this is the integrated circuit containing already 4 gates, and these are the extra 3 gates, the SMD guys that you are seeing here. And yeah, it's looking interesting. It's looking interesting. A little bit big. I'm trying my best to make everything as small as possible. I'm not using through-hole components like resistors, transistors, or capacitors. I'm only using SMDs. I'm using through-holes, only these large chips, integrated circuits, because they are all that I have. I don't have the SMD versions of these larger chips that I'm having here. But excepting these, I made my mind to make everything with SMD for a very small footprint in the end, for a very small circuit. But it will be big. It will still be a big circuit, even if I'm using SMDs, especially those here. I have no idea if I will even build this block here with all these converters. I am absolutely not sure. I'm not completely sure how I. But this is a very, very interesting challenge for me, because I did buy very special diodes, SMD diodes that are looking exactly like a SMD resistor, 1206 case. I have those diodes for more than a year prepared, put aside to use them in their SMD forms, and now probably this is a very good time to actually implement them in this converter circuit that I'm using almost all the times in most of my circuits. And yeah, I will see how that will work, if it will work. If not, like I said, I'm not even sure if I will use all this block here, the lower side. I can perfectly, it is perfectly fine to make the top circuit here, and it will work fine without this bottom one. Without this bottom one here. And yeah, I can separate them, but I really wish to make them as complicated as they are. It is a bit way too complicated just to fucking beep. Just to fucking make a beep. It's way complicated, and I can't wait to see how it will look. I'm very extremely undecided how I will link here in the 3D, if I will go the long road and actually link everything, every wire to every pin that I'm having there from every gate output, and then the inputs and everything. Holy fucking shit. The wiring is criminal. It's criminal. It's pornographic. It's real porn here. what I have to do at the wiring level. I hope you like everything you've seen so far. I hope you like my ideas. I hope you understood what I'm building here. And let me get rid of this guy here. We don't need you anymore. Thank you very much. And yeah, not you also. And also you, not you. Yeah. Oh, this is it for this movie. Thank you very much for saying and watching and listening and paying attention and understanding what I'm doing here. I really hope you like what I'm making here. And we will see each other on the other side when I will actually build something. I have no idea how I will make it and how it will look in the end. I am very curious. I'm more curious than you guys, those who, if they are watching my movies. All right. Thank you very much. This is it. See you later from your favorite artist from Romania, Mr. Q12. Bye bye.